Michael Stifel, who lived from 1487 to 1567, noticed a pattern that he referred to as the law of exponents. He noticed, for example, that you could take two numbers like 4 and 8, which multiply to give you 32, and if you look at the exponent that you would put on that you would put on 2 in order to get that number, in other words their power, I guess, their power of 2, that you would add those exponents to get the result. So this would be 2 plus 3 equals 5. So 4 is 2 squared, 8 is 2 to the third, 32 is 2 to the fifth. So these exponents add. What he was noticing actually is that their logs add, which is something he didn't know about yet because that word hadn't been used yet. But we could say log base 2 of 4 is 2, plus log base 2 of 8, which is 3, equals log base 2 of 32, which is 5. So when we multiply numbers, their logarithms add. We could also look at the same thing with dividing. So for example, let's say I took 128 divided by 4. Well, 128 divided by 4 is 32. You can see it, 4 goes into 12 3 times and 4 goes into 8 2 times. So if we look at those numbers on here, there's 128 and there's the 4 and there's the 32. So notice the exponent for 128 is 7. The exponent for 4 is 2. If we subtract those, we get the exponent for 32, which is 5. So we could say log base 2 of 128, which is 7, minus log base 2 of 4, which is 2, equals log base 2 of 32. So notice when the logs, their exponents subtract, or when we subtract their logarithms, we get the answer that is the division of these two numbers of 128 divided by 32. So how could we apply this to something, kind of practical? Well, let's say I wanted to multiply two large numbers. I wanted to multiply 512 times 2048. Well, I could look that up in the table and I see here's 512 and here's 2048, and I just look at what their logarithm is. The log base 2 of 512 is 9. The log base 2 of 248 is 11. I add the logarithms and I get 20. So that means that the answer when I multiply is just going to be 1,048,576. So that's a lot faster than multiplying it out by hand. It's a shortcut. I could do the same thing with division. So let's say I want to take this big number, 524,288, and I want to divide it by this number here, 16,384. Well, I look at their exponents and I subtract them. 19 minus 14 equals 5, so the answer is 32. So this gives me a nice shortcut, and this is a shortcut that was really useful to mathematicians and scientists. And you might think, well, what if I didn't want to multiply those particular numbers? Well, this also works for decimal values of the same number. So for example, if I wanted to do 5.12 times 2.048, I could just take I would get the same result only with a different decimal place. So I would just look at 5 times 2 and say, oh, that's about 10. So this must be 10.48576. So using a little common sense, you can apply this to numbers that are decimal numbers or larger numbers. Another thing we could look at is powers. So if we look at log base 2 of 4 to the third power, well, 4 to the third power is 64. That's the same as log base 2 of 64. And log base 2 of 64 is 6. But I could also bring this exponent out front and say this is 3 times log base 2 of 4, which is 3 times 2, which is 6. So this is another way I can use this table to help me kind of figure out some logs in a simpler way. Now this of course is just a very small little sampling of some different logs in base 2. and that wouldn't be generally useful unless you happen to be wanting to use these particular numbers. So another mathematician built on the work of Stifel, and he came up with the name logarithms, which stand for logical arithmetic, and the decimal point notation. He spent his entire life, pretty much, his 20 years of his life, calculating an immense table of logarithms, doing over 10 million calculations by hand, and then people were able to use his table to do these kinds of shortcuts. A contemporary of his named Henry Briggs first used the common base 10 logarithms, and he improved the log table until it looked more like this. So this is a base 10 log table. Basically what it says is 10 to the 0 equals 1. 10 to the 0.301 gives me 2. 10 to the 0.3031961 would give me 2.01. So this is the exponent in bold that I would put on 10 in order to get this number. So since you can apply these calculations to things with different decimal points, all I really need are all the numbers from 1 to 10. So from 0 to 9.99, and then scientists could use this, or students. When I was in high school, a 4-function calculator that just added, subtracted, multiplied, and divided, didn't really do anything else besides that, cost $100, which in today's dollars would probably be more like $300. And so students didn't have access to calculators. They were too expensive. So we had to do our logarithms using a log table. So I learned to use logarithms using log rules and a log table like this. For hundreds of years, a log table like this simplified calculations for generations of scientists and mathematicians. Now another thing that the logarithms were used for was also a slide rule. A slide rule was a computing device based on a logarithmic scale, and I honestly can't tell you exactly how it works now. I just know if you look at the scale, you'll notice the numbers are not evenly spaced, and that's because it is based on a logarithmic scale. The numbers on some of the scales are and some of the scales are not. So I wrote down the instructions of how to multiply together two numbers using a slide rule. I used to use one of these in high school to do my chemistry homework, so any scientific homework you would do, you didn't have a scientific calculator, you had a slide rule. And we didn't use calculators at all in math class, even in calculus, so consider yourself lucky. So if I wanted to multiply 2.3 times 3.4, first of all, I would move the cursor on the D scale to the number 2.3. Okay, so there's 2.3. And then I would slide the middle thing here so that the leftmost 1 is on the cursor, which is that vertical line. Okay, now I'm going to have to move the slide rule over so you can see over here. Then I'm going to move the cursor again till it lines up with 3.4 on the C scale. So I have to keep moving it a little farther over. So 3.4 on the C scale. Then I read down on the D scale that the answer is 7.8. Okay, so that was just one of many different calculations you could using a slide rule. I learned how to do one of these very well when I was in high school. I really don't remember now. I had to look up the directions even to do a simple calculation. If you look at the movie Apollo 13, if you ever happen to see that movie, it's about a trip. It's about one of the space missions to the moon, and there was a problem with the spaceship, and there was an explosion, and the astronauts had to repair their spaceship, and then they had to redirect it to get back to Earth because they had been blown out of the correct orbit, and they were not in line to get back to Earth. So you can see the scientists at NASA pulling slide rules out of their calculators to do computations to help the astronauts get back to Earth, which is really interesting. Now, of course, these are obsolete now. We have calculators that do things for us like this, so we don't use the slide rule. We don't use the log tables anymore. So what are some more recent applications of logs? Well, of course, we can use logs to simplify and solve exponential equations. We can use them to linearize some nonlinear functions, and you're actually going to see kind of an example of this. The reason you would do that is to create, because a linear function is easier to work with than a nonlinear function. In the same way, there are certain scales of numbers that are very unmanageable to work with, but we can make them more manageable by using logarithms. And one of these is the measurement of loudness of sound, called decibels. We learned when we talked about sound that basically sound is created by an airwave pressure on your ear that makes your eardrum vibrate. Well, it turns out that the smallest amount of pressure that causes an audible sound for the average person is 10 to the negative 12th watts per meter squared. Very, very slight pressure. It turns out that 10 to the 4th, or 10,000 watts per meter squared, would result in the perforation or the breakage of your eardrum. So this is a large scale of starting with the lowest amount. So if we would call this a 10 to the 0, which is 1, that would be the very lowest pressure. If we rescaled and said we rescaled 10 to the negative 12, and we'll say that's our lowest pressure, we'll call that 10 to the 0, then that means our highest pressure would be 10 to the 16th, because the difference in multiples of 10 from 10 to the negative 12 to 10 to the 4th is 10 to the 16th. So this is a very large increase in pressure from 0 to 10 to the 16th. 1 with 16 zeros after it. I don't even know what that number is called. So I don't want to say, oh, I've got a 1 million, a sound that's a million in loudness versus a sound that's a billion in loudness, or whatever that number is. I don't even know what that number is. So to make the scale more manageable, we took the log of each one of these numbers. Log base 10 of 10 to the 0 is just 0. Log base 10 of 1 is 0. Or log base 10 of 10 to the 1st is just 1, and so forth. So I'm just using the decimal places on these base 10 numbers to create a scale for sound. And of course there would be sounds in between these loudnesses too. And since there would be sounds in between these two loudnesses, like a sound between the loudness of rustling leaves and a whisper, then that would become a decimal number like 1.2 or something. So to keep from using as many decimal places, the bells were multiplied by 10 and became decibels, or decibels. So we say this is a 0 decibel sound, this is a sound of 10 decibels, 20, 60, 80, and so forth. And this is our scale for measuring loudness. What's interesting about this is if you go, for example, from a whisper to a normal conversation, that's a 10,000 increase in pressure, 10,000 times increase in pressure, but it's only a 3 times increase in decimal. Interestingly enough, even though it's 10,000 times more pressure, we hear it as 3 times as loud, so we hear logarithmically. Okay, so now going on to the next example. It's a Richter scale, and actually our last example. The Richter scale is a scale for measuring earthquake intensity. Once again, intensity is not measured in a linear scale. This is a logarithmic scale because the amount of vibration from a small earthquake, which just barely vibrates the ground, to a very huge earthquake, which causes buildings to topple and cracks to appear, goes from a very small amount of amplitude of motion. So think of the ground kind of going up and down like this when the earthquake hits. So we're talking about the amplitude of the motion. So if it's a micron is a very, very tiny measurement. So we're saying it's barely moving at all to it's moving up and down a billion microns. That's a huge earthquake. So once again, since the scale goes from 0 all the way up to 10 to the 9th, such a big scale, what the Richter scale does is it just takes the power of 10 and names that as the earthquake scale. So 1, 2, 3, 4. So we say a magnitude 7 means it's 10 to the 7th microns of movement. So when we look at an earthquake that goes from, say, 6 to 7 on the Richter scale, it's 10 times more intense. So we see here, these are very small earthquakes here, a moderate, strong, and it tells like when you get up to 7 to 8 on the Richter scale, great devastation, damage. There's some damage, moderate damage from 5 to 6. It's very rare to find something higher than 7 on the Richter scale. There's only been 3 in the history of the U.S. that have been above 8 on the Richter scale, and they're listed down here. New Madrid, Missouri is the one that's closest to us, so we're actually near an earthquake fault that has been inactive for quite a long time. I remember I remember a couple of earthquakes in my lifetime that have been very minor, but nothing major. But there was a huge one in 1812, and there's actually a rest stop on Highway 57 in Missouri that you can go to that commemorates the New Madrid epicenter of the earthquake, and it was a very good example of our taxpayer money being used to fund something relatively unimportant that cost a whole lot of money. But if you ever have a chance to see that particular rest stop, it does have a little museum to the New Madrid earthquake. So these are what the current uses of logarithms are: to rescale data as well as to solve exponential equations.